Yeah, I haven't speaking English for quite a long time because the bad situation in the world. And I will try my best to make the presentation fluently and clearly. Okay, let's start. Okay, first, the first thing is that we have put the slide in the GitHub page here. Yeah, you can check up the link. And the assistants also put the web page into the chat group chat of the Zoom. Yeah, you can check the latest version of slides here. And this is the big outline. The tutorial will contain 5 parts, and in the first part, I will mainly focus on automated machine learning and introduce about core problem in AutoML like organization and generalization, and why the automated machine learning is a lead and a trend for nowadays machine learning research for applications. And in the second part, Professor Lee will talk about why and how recommendation system needs AutoML, or AutoML can help build better recommender system. And in the third talk by Mr. Qiang, he will introduce some recent works by Tsinghua FIB group or our company's for Paradigm to show some recent advance in automated recommender system. And in the fourth and the fifth part, we will take one step further to consider how graph neural network and the knowledge graph embedding can benefit the recommender system. Yeah, that's the 5 part will be covered in today's tutorial. Okay, this is the first part, and I have shown the email address in the screen. Yeah, and the right below part is also my personal chat. Any question or discussions are welcome to send either in person by the chat or by the email show above. Okay. Let's start with a very general and a fundamental problem. Okay, first, what is machine learning? We have a very classical definition on what is machine learning, and it is also defined, perhaps introduced by Tom Mitchell in a book 20 years ago, named machine learning. Yeah, basically, machine learning is specified by ETP. E is experience, T is task, and P is the measurement. And machine learning is also a sub-area currently is a sub-area in computer program. Maybe in future it doesn't, but currently it is. So take image classification as an example. For experience, this is the ImageNet, not image classification example. Yeah, for the experience, the images are the input to the system. So it is the experience. And the task is to classify whether the image contains a cat, a dog, or a car. So the final performance measurement is also by testing accuracy. So this is the fundamental 3 elements in machine learning. Okay, based on this definition, core issue in machine learning, as we can see in the left part of the screen, this is also the image, very simple pipeline for image classification. First input, then we have a classifier F, or more formally a hypothesis F. Here is a CNN to do the learning task, and then finally to do prediction. So Here we have two fundamental issues in machine learning. First is about generation, how to generate good prediction using a classifier, and how to train the classifier efficiently to generate such good classifications of such good prediction results. So, and currently generalization and optimization are coupled with each other in the era of deep learning. Traditionally, it's more somehow dependent with each other in supervised machine or decision tree. Anyway, okay, but there is a big issue in machine learning, or there are some fundamental principles underneath the machine learning. Basically, we have PSE, probably PSA learning theory and low-fee launch theory. First, from computational perspective, probably approximate correct. Theory tells us that not all learning problems can be efficiently computed by computers. And from statistical perspective, low-fee launch tells us there's no single algorithm can perform good on every kind of problem. So in order to use machine learning well, we need much prior knowledge on the learning problem. And so here is how we use machine learning from computer programs in practical. First, from left to right, we have problem definition, data, feature, blah, blah, and finally development. So the data and the problem definition need to define by business demand or human expert. And for the feature model optimization evaluation part can be processed by machine learning. And on the feature level, the fundamental question is how to represent the learning problem. A very easy case is that we have scalar vector matrix or tensor representation for a certain kind of learning problems, and we need to determine how to represent those features. And once the feature is determined, we need to find some good classifier to operate on those features. Two very popular classification, CA or RN, yeah, it depends on the problem and which one is to be used. It needs some prior knowledge. And finally, after the classification has been chosen, we need to perform optimization for the classifier. So two very popular algorithm, SGD, stochastic gradient descent, or its variant, algorithm. Yeah, we need to pick one of, we need to try some of the algorithms to use the optimization. So fundamentally, it is a trial and error process. We need to repeat this process again and again in order to achieve cheap computation and better learning performance. So in a word, machine learning equals to data plus knowledge. And in order to generate from seen to unseen data, we need prior knowledge. And in order to build some classifier from the data, we need optimization. And we need optimization, and we need the data. So this is a very short summary of how we use machine learning classifier or machine learning models. Okay, there is a very fundamental trade-off behind all about principles. Very briefly, whenever we have a learning problem and whenever we have a learning problem, we can see this is error bound here. And this error bound means that if we have larger hypothesis, and which means a classifier have larger ability to learn for some classification problems. It means this number will grow larger. And then, as a consequence, in order to make the generation error small, we need to have more samples, and which means we need to collect more training data. So currently, we are more likely to use large classifiers and then use more training samples in order to obtain better learning performance. So this is a fundamental trade-off underneath the machine learning classifiers. So let's take one step further to see how the error or the generation error can be decomposed in those machine learning classifiers. Given any classifier, this is the initialization, and we need to perform optimization part so we can get our empirical best estimator, HI. And then when we have infinite samples, we can get the best classifier in our hypothesis set. This is head start. But from practical perspective, the guard model will never lies within the set of our hypothesis, which means the head edge. So the total error is decomposed by approximation, estimation, and generalization. And generally speaking, the approximation error here is determined by the prior knowledge, and the estimation error here and the optimization gap together here is more determined on the training data. I will show more reason why I need to emphasize and give some explanation over such an error decomposition. So, okay, let's back to a very high level of why such things will be happen or why we need more samples or larger hypotheses, because we can look back to machine learning history. This is a very short, brief review of some classifiers designed in the history. Like in about 40 years or 50 years ago, we have expert system, and these systems are more rule-based. And then we have support machine, and more recently we have deep learning based. And we can see from these trends, we are more likely to use larger hypotheses, which means we are more likely to use more complex models. And then as a consequence, the optimization is getting more complex. And nowadays, the optimization is also coupled with generalization. And in order to make such complex learning system work, actually more and more prior knowledge is encoded in the learning process. And as we can see, currently in rule-based system, our prior knowledge is encoded directly into the feature level, like the pixel of an image. But in the deep learning, in deep learning classifier like CNN, we will have a very high understanding or a very high abstraction of image pixels by feature maps. And we can also have a very meaningful visualization of those feature maps. So the prior knowledge helps us to build more and more stronger classifier, and the prior knowledge is also imposed on more abstract level. Okay, fundamentally, let's get even longer ago. Actually, we will perform experiments and we will have our hypothesis on our model. And actually, this is an iterative process and deeply rooted in the statistical science. Like this is what This is a description on the wiki for Ronald Fisher, and these two images are also copied from this famous article. And in this article, we also have a very famous sentence, almost wrong, but some can be useful. And this is also an illustration of pack-learnable theory and low-fee launch theory. Okay, after a brief review of machine learning and what we are doing along the years in the topic of machine learning, now let's take one step further to look at what is automated machine learning. Okay, to explain what is automated machine learning, let's first look at simple examples from automation. When for boil water or robot arm or automatic drive, they are all actually very simple example of control with feedbacks. Like if the temperature of the water is nearly 100, and maybe we have some sensor to cut off the fire or cut off the electronics. So then we will get well-boiled hot water. So in automation, actually, we wish fewer and more understandable interface follows to human beings, and then we wish the controller, like maybe the sensor here, to interact with underneath processing in a more robust and stable way. So take the similar idea, let's look at the pipeline of the machine learning application. In previous slides, I have mentioned that in order to make machine learning work, we need to encode prior knowledge in many perspectives of machine learning, like the feature selection, the feature selection, how to represent the learning problem, and how to pick up the right model for training, and how to perform good or efficient optimization for the classifier. So in a very high level, the goal of automated machine learning is try to reduce of humans in the low level, try to replace low level problems in the about trial and error process of machine learning. And this is okay. This is just the idea of very general idea of what is machine learning, what is automated machine learning, and why it is a trend or perhaps or must or need, because we can see the investment in AI industry is yearly exponentially grows every year. And we have many applications in different industries, like retail or medical or some face recognition or the oil industry. So we have many applications need to be developed in the various industries. So the demand of machine learning usage is very large. And also we can see this is from the right figure. We can also see the demand of proper staff skills can also be a very critical problem to develop such applications. So the AutoML can be both of industrial value and academic value to nowadays gentlemen. So, and in the following slide, I will show more example I will show more details on the industrial perspective and academic perspective. And now let's first start with an industrial review of the machine learning. Okay. Compared with previous slides, we have a gray box here. And actually, the ultra goal of automated machine learning is to replace the feature, model optimization, and evaluation part finally by a controller. And this controller can be realized by a computer program. And then the human can focus on problem definition and data and the application development, which can be of much more business values rather than those technical details. And actually, we have many commercialized examples from AutoML techniques. These are very two simple examples of how AutoML can be applied. The right part is the auto sklearn. It tries to build proper ensemble of classifiers, and simply it tries to turn hyperparameters in a more efficient, in an efficient way, so that better prediction accuracy can be obtained. And the right part show example on how features can be generated in tagged data. For example, the A, B, C, and D are two discrete categorical features. And there is one very strong pattern to generate new features for category features is to do cross product among those features. So we can see this is A, B, A, C, C, D, and we have a third order interaction of A, B, C, B, C, D. So this is the left part show how hyperparameters can be properly configured for machine learning application. And the right part shows how features can be automated enhanced for some tagged data applications. And here is more examples of commercialized examples for AutoML products and applications. The tables on the left is kind of out of date. These are based on statistics up to nearly 2 years ago. And here the right part shows some companies which put many investments into the techniques of AutoML. So based on the above two examples, we will turn back to see a very brief definition of AutoML program. We can see the AutoML is fundamentally an interaction of three areas. So first, we need to build some proper hypotheses for learning from the data. So it interacts with the machine learning, and we need to, when we try to learn, and when we try to effectively learn from some certain data from certain domain, so it also interacts with the data analysis. Finally, we want to drop more and more low-level privilege from the usage of computer machine learning programs. So it also interacts with automated control. So in a very high level, we can see this is the iterative process of most AutoML methods. We need to determine the subspace or the configuration space for the AutoML controller, and then the controller process is the control with the feedbacks, just like boil the hot water. And finally, we need to get performance measurements like testing accuracy or how much memory or how much flows that a computer programmer used in order to evaluate the feedbacks. Okay, now let's look at one step further. In previous slides, I have talked about the industrial value of AutoML, but AutoML is not just about industrial applications. And in previous slides, I have shown how the generation error can be decomposed for classical machine learning classifiers. And I also show this figure on the left part of the screen. And actually, from this perspective, from feature classifier and optimization perspective, we can see the AutoML program tries to directly minimize the total error of using some machine learning algorithms or classifiers, which means this part contains optimization and this part contain classifier selection. And this part can contain how to represent the features or the target. So this is a graphical illustration of how classical ML can be compared with AutoML. The figure is adapted from Murray's book, Foundation of Machine Learning. And in classical machine learning, this is the God model, which is denoted by edge bias. And this is, in classical machine learning, we are comparably, we are searching a relative small hypothesis class because we will not search the architecture of the neural network, or we will not try to build a big ensemble. So in the left part or the right part, we can see the hypothesis class of the classifier can be much enriched. And currently, since we also have much stronger computers and much bigger computer resource, so we can use those computers to search in a larger hypothesis. But the most important thing is that this hypothesis can be parameterized in a higher level. I will show some example in NNS later to show why this is important. Because if we cannot represent this larger class of hypotheses in a mathematical way, it's not possible for computers to do some subsequent computations. So let's continue previous figures. Okay, we can see from rule-based to AutoML-based, the low-level human knowledge on data, model, or features are more and more replacing by computational power. So in this sense, the AutoML approaches can be seen as a successor of machine learning trends. And also, this part of opinion also coincides with Professor Benju's talk, deep learning from system 1 to system 2. Yeah, system 1 do not have cognitive ability yet. So, but the AutoML is also from lower level to a higher level, but from a different perspective. So this perspective try to parameterize the prior knowledge on a higher level so that the lower level part can be replaced by computational power so that less and less human assistance are needed in the usage of machine learning programs. Okay, this is the academic value and the industrial value part of the AutoML of the AutoML approach. And now let's look at where we saw. Let's look at the perhaps the most famous, popular, and famous example in the area of AutoML, which means neural architecture search. The figure is extracted from this Google's ICML 2019 paper. As we can see, the red curve is the architecture identified by new architecture search methods. We can see also the blue line is also obtained by some other NS approach, but the red one is overviews much better. So we can see with the help of AutoML techniques, we can hopefully we can get much higher performance, like the right figure show on the ImageNet. and a much less number of computations, which means the model can be smaller but stronger. And why the NNS lead? And why the NNS has become a lead for machine learning applications? The reason is also very obvious, because the left part is also is actually show a very simple example of AlexNet. For such easy and for such simple CNN networks, we already have many hyperparameters, like number of filters, filter width, height, stride height, width, and skip connections. And for more complex one, it's not possible to design some very good architectures. So nowadays, the design of neural network architecture has more and more replaced by NNS methods. And we can also see some the below part shows some reference in this area, and we can see there are three major paths in NS approach. The first is the what space to be searched, CNN or RN, and also we need to determine some search algorithms like ENS, this one, efficient neural architecture search by parameter sharing, or currently a very popular differentiable one like DAS. Yeah. And the third part is that since we have an evaluator we need to get some feedback from under these applications. So we also need to find some evaluation methods. And these are the three parts of the NIS approaches. And actually from the year of 2016 to 2018, these three paths have finished one cycle. All of NS reduce the search space, fast evaluation, and fast search algorithms. And now it starts another new round. So we can see in the efficient net, it encodes the search space in a better way, scale from smaller model to large model. So we can see much better performance can be obtained compared with the approach in the first cycle. This is the second cycle. Okay, and actually AutoML is not just about architecture search for CNN. Our group has also tried some new directions like the usage in knowledge graphs. The KG means knowledge graph, and Yong will talk more details about those two methods perhaps 2 hours later, about 2 hours later. So, and we can still see the trends, and the trends are the same. Actually, we are trying to push the complexity smaller and smaller, but also performance higher and higher. But obviously, the AutoML is not just about performance. It's also about the understanding of underneath data, the understanding of underneath search algorithms or models. We need to try to use computers to help humans to understand the underneath problem on a higher level, so that we can get mass complexity and better performance. Performance is not just the only goal of AutoML, but it also tries to help us understanding the underneath domain and data better. Okay, now we turn to the third part of this tutorial, of this talk. Okay, with so many methods and with so many citations like here, and with so many historical process like here. The next question is that, is automated machine learning really new? Actually, this is just, okay, the third part is more based on my personal understanding. So is the AutoML really new? Actually, my first answer is no, because we can see these references are all closely related to the problem I have previously mentioned, especially for the new architecture, for the design of new architectures. It is also a very hot topic, hot popular 20 years ago. So, and these are all some topics highly integrated with AutoML recently. And we can also have a closer look at more recent examples like AutoScanner. This is a bi-level problem, and this is thus. This is also a bi-level problem. And actually, the right part shows an example of bi-level of meta-learning to deal with noisy labels. So we can see on the formulation level, they are quite closely related. We have a higher level and a lower level, and we can also have a higher level here and a lower level here. So they are much alike with each other. And we can look one step further of how meta-learning is defined in the literature. We can see these are the 4 classical definitions. And okay, let's see the second one. The primary goal of meta-learning is to understand the interaction between the mechanism of learning and the concrete context in which mechanism is applicable. So this point is very closely related with the one I previously have mentioned. AutoML is also a tool to reach better performance and better understanding of the underneath mechanism of the learning process. So is AutoML just an application of meta-learning, model selection, or bi-level programming? Here I mainly throw a question out, but personally I don't have a very concrete answer to this question. But hopefully I can give some. Here is also what I thought. Okay, again let's took the third picture out of this very old paper. Actually, the facts and the hypotheses are at the iterative process, and the facts will become more precise, and the hypothesis will become more stronger during the iterative process. And during the process, we have different moving windows in different decades. Like here, the word experimental design. And here's also why the technique is also evolving, and like the rule-based, statistical-based, deep learning-based, and currently now the AutoML-based. And the more technical details will be explained by my colleagues in the following talks. And here is also show the AutoML is also the moving window in the techniques around next few years and the past few years. So it is evolving techniques for just better generalization, and we also try to promote stronger optimization methods to reach such better generalization. And from the academic perspective, and currently especially due to the large investment in the AI industry, the industry needs AutoML further because we can see the figure on the right part. The AutoML, the computer program, can help humans focus on basic demand and values, which can be of larger interest for non-experts out of machine learning community. And in this way, more and more industries and more applications can be empowered by machine learning techniques. And finally, the last part of the talk is what we should focus the next. And in previous slides, I have shown, this one here. Using NS as an example, as we can see in the from 2016 to 2018, it has finished one cycle of the evolving of the techniques from space algorithm to evaluation methods. Now, let's see what we should focus on next. Okay. Because, okay, indeed, large samples will not always indicate stronger performance, but for many industrial applications, it is indeed the practice to solve the learning problem. So, as we can see, when given a task, when given a certain task and a data, we try to build larger models on bigger data. So the model size will grow larger, and also the sample size will grow larger. And this is the technical roadmap of, and the right part shows some technical roadmap of the old ML approaches, search space, search algorithm, and evaluation methods. And we need to push these three directions simultaneously forward in order to operate on larger models and larger data. So this is a very brief summary of the next focus. First, on the search space, we will have old tasks. By old task, I mean design and search of thin architectures. And we will focus more on how to scale up small models to larger ones, because directly search on large models is too expensive. And also, we will try to come up with better way to transfer model from smaller data set to larger data set. Yeah, but the problem is how to design good transfer learning methods to achieve this goal. And except from above all the mentioned tasks, we also have many new tasks which AutoML can be operating on. For example, like the processing of hyperspectrum image and the architecture of natural text classification, and also some tasks my colleagues will talk about later, like the design of Qiang's architecture or the design of logic graph embedding methods. So we need to find some really interesting and really important search space in order to operate on AutoML methods. The point is again on the AutoML is not only try to boost better performance, but also we try to throw some light upon how the model and how the search space can help design future better, stronger models. And that's why and how human can focus on a higher level of prior knowledge on underneath data or underneath the learning process. And for the second perspective, like the search algorithm, okay, the first one is that like the very popular search algorithm like DART, it directly search in a supernet. But actually, we can have various constraints, different constraints, and these constraints are determined by the search space. And this constraint need to be included in the supernet for search architectures. There are some recent developments in moving this direction, like single path one shot. There are about 20 or 30 papers. So with this kind of problems introduced by DAS. So the applicability, how to handling the various search constraint in the space is very important problem. And this problem is highly depends on the new task and the search space. And the second part is that, okay, now in the AutoML, we are operate on a bi-level problem. On the first level, we are searching architectures for tuning hyperparameters. on the lower level, we are training the classifiers or the training deep neural networks. And actually, for each iteration, each iteration in such the tuning process is very expensive. So compared with classical optimization methods, we are more focused on efficient mini-batch training. Here, we are more focused on the faster convergence rate, or how good the convergence is can be introduced by different search algorithms. So how to promote good, better search algorithms can find a better local optimal and stronger search guarantee is a very interesting direction of AutoML approaches. And finally, for the evaluation part, okay, a very classical method to evaluate the lower level performance is by just train the model once. Yeah, it is the standalone method. But the problem is also very obvious. For ImageNet, we perhaps need 1 week to obtain the feedback, so it can be too expensive. And parameter sharing is a very, very popular approach to do fast evaluation. But however, what parameter sharing optimize and what parameter sharing generalize is a very problematic, perhaps not problematic, is a problem that not very clear. So how to understand parameter sharing is also a very important direction for future AutoML research. Okay. Okay, this is the end of the first part of the talk. Okay. Let's turn back to the first page. So from what is machine learning to what is automated machine learning, and how automated machine learning is connected to some history approaches. And finally, we have just briefly talked about what we should focus on AutoML next. Okay. And for questions, for discussion, I'm very glad to discuss with more details offline. Yeah, because my English is not so that fluent to be able to answer those questions online. So if you have any questions or discussions, please send email to the following address. And if you have WeChat, you can also add my personal WeChat shown here. Okay, thanks.
Yeah, I had a quick question about like automated, like feature engineering, automated, because like a lot of the techniques are like, you pull some data from a database and then the AutoML starts using that data that you already pulled. But like really, I think the real power in AutoML, just from an industrial standpoint, is being able to do more of the data science pipeline, like that, selecting data sources and really constructing pipelines automatically from those data sources. Like, what are your thoughts about that?
Yeah. This is indeed a very, very good question. Yeah. That is also why I mentioned there's no good machine learning algorithm can operate on all different kind of data good, right? So this is just some experience from our company. And there are two. First, we need to look inside a very different kind of industrial problems. So for example, the example I shown, that auto course I shown here, it can successfully operate on tabular data from banks. And this is also one of the major products from our company. And indeed, if we use the same method for some CTR requirement, the performance will not be that good because indeed, as you have mentioned, the data engineering part is very complicated. So we need to build some different automated feature constructing tools for different kinds of needs and applications. This is the first approach. And the second approach is that also I learned from our company is that we will try to join many cargo competitions or code lab competitions. We will collect some very good practice from participants or our colleagues, and thus we can construct some rules to generate those features. And these rules can be somehow automated. But indeed, as you have mentioned, it is not that general approach. Indeed, when we deal with some new kind of applications, we need to look much deeper inside, and then the automation part of the feature construction can be possible.
Yeah, I'm just thinking about it more because it's like if we treat like each component of that machine learning pipeline as like as its own parameter space, then it's like you can have potentially like an AutoML for each parameter space, and then like a meta AutoML, deciding between them, or treating each segment as its own parameter space.
Yeah, indeed, yeah.
But then it's very, it's one thing to actually to write it down and in theory, but then it's like to run it. You might be able to find an answer, but how long will it take to run it? The runtime complexity. It's like you might have to wait like 100 years to search the.
So in our company, the AutoML system is getting more and more complex. We try to build more and more tools and components into the system and make the system customized to different industries. Yes, if we try to work on the higher level, many computational resources are needed. Yeah, that's a very big problem.
Yeah, that's a huge problem. In industry, because like I'm both in research and in industry, and I've seen like really the a lot of the industrial applications for AutoML are using like open source stuff, and there's not much value add in terms of the complexity. It's just more about like throwing more GPUs at the problem, or throwing more nodes, but it's not really solving the problem any quicker. And it's like the costs become very there's not really much emphasis on containing the cost of these systems. It's like you can get an answer, but you have to pay a lot of money to get that answer.
Yes, that's also why stronger search algorithms need to be constructed. And indeed, there are many frustrating perspectives in this domain. Yeah, I can only say this is an interesting promising and somehow can solve some very important practical issues. But on the other hand, as you also have mentioned, there are many very long way to go.
Yeah, because it seems like we need faster algorithms, but also like I think new ways of thinking about how to phrase these problems. Like maybe we're not phrasing the problems in the way, maybe we can simplify the problems and then use some other techniques.
Yeah, okay. Let's turn to, thanks for your question. Let's turn to the second speaker.
Hello. Okay, can you hear me?
Yeah.
Yeah, actually, following the talk given by Dr. Yao, introduced the basic ideas and advanced progress about AutoML. I would like to introduce some basic ideas about recommendation systems and latest work about recommendations. And more important, I will introduce combine the AutoML with a recommendation together and explain why we need AutoML in recommendation systems. Yeah. First of all, I would like to give a short, brief introduction about myself. And I'm Yong from Tsinghua University, and we are in the Department of Electronic Engineering, and we're running a data science and intelligence group in Tsinghua. And our group, the focus of our group is recommendation system, AutoML, and urban computing. Yeah. This is the outline of my talk, and I will first introduce the basic idea about recommendation system, and then I will talk about the recent advance in recommendation systems, including the how we apply deep learning and how we apply graph neural networks in recommendations, and by introduce the several of our latest work. And finally, I will combine the recommendation system and the AutoML. I think every one of us should be very familiar with recommendations. Yeah, because we interact with the recommendation system every day with all kinds of products provided by the internet. The basic idea about recommendations is come from the area of information retrievals. The old fashion of information retrieval is search. But actually, when we have a lot of more and more items in the internet, and sometimes we don't have ideas about which kind of information or items we would like to interact, then recommendation system is very important to recommend something actively for a user. For example, when you are browsing a e-commerce website, or you are looking at a short radio applications, you don't know what you would like to look at, then the system, it is very important for the system to recommend something for you. Yeah, and then the basic idea is that when a user interact with a app, and the app need the interactions, including you click something in your app, or you have show your interest in the app, or you have some friends following in the apps, and then the app can collect the data about the user preference, and from the data we can build the recommendation models, and then we can know we can predict what's your interest, what is your preference, and which kind of item you will like. The recommendation algorithms will recommend top K items to a user. Following these ideas, the most important ideas about the recommendation system is it is used to model users' preference toward items based on the user history behaviors, and including the click like follows. And we can formulate the recommendation problems in the following way, actually. The input is the history user item interactions or additional side informations. The side information can include any kind of information about users or items. For example, for the user profile, it can including the basic demographic information, including ages, female, male, or some others. For the item profiles, including any kind of information about the item, like categories, or the price, or any kind of things you can think about it. But the basic information here is the user item interactions, which items the user have been interacted before. And then the output is the system need to giving a target item. The item can be any kinds of things you interact in the internet, like movies, songs, products. Yeah, the system need to infer how likely a user would interact with it. The interact also including different kind of behaviors, like you will click the item, you will view item, or purchase item finally. Then in order to solve this problem of recommendations, we need to design different kind of algorithms in the systems, and in the current recommendation systems, the basic framework or architecture is very similar, because along with the industry progress about recommendation systems, even we have different kind of algorithms in different company, but the framework shown in this slide is almost the same. Yeah, from the product to the user, we have two phases to do recommendations. Yeah, the phase one, we code it as candidate generation, and phase two, we call it ranking. And for the phase one, the model is it also models the problem as a problem of collaborative filtering models. And the phase one, the candidate generation is to select the product from millions of products to hundreds of products. And phase two is first to ranking all kinds of products, hundreds of products to tens of them, and then show the tens of items to the users. Then finally, the system can select millions of products to select tens of products from millions of products to the users. And for the phase two, the recommendation models are called feature-based models. Yeah, for the data source, for which kind of data we use in the phase one and phase two is also very different. For the candidate generation, the most important data is the user interaction history. As I mentioned before, this kind of data source is most important to show users interest by the history information. And for the phase two, we need to do a more precise ranking. Then we can combine different kind of other informations, including the use profile or item profiles, or including both. Even we can include some context information to do the ranking. That means to the rank two, the phase two will use more informations. Yeah, this giving the basic problem descriptions of recommendations, and also a basic system framework about the system about the recommendations. Yeah, I only introduced the basic idea about recommendations. As I learned that if you are joining this work, because we are talking about advanced recommendations, you should know some ideas. We just recap for the whole systems. Yeah, the second part of my talk, I will show some recent advance in recommendations, including deep learning and graph neural networks. Yeah, this is also the latest progress in recommendation systems. I first introduced the latest progress about deep learning for recommendations. Actually, in currently recommendation system designs, including both in the academic and the industrial systems, the deep learning is widely used for the recommendation system designs, including the feature instructions to do the representation learning, to learning user inference, preference, and item profiles, and also finally to do the matching function learnings, also using deep learning. And the main reason is that the deep learning is showing great powers in modeling high order similarities in recommendation systems. The most important information here is that because we need to use more and more information and consider more facts about user preference, and then we need to model the high order similarity in the systems, and in such kind of high order similarities or non-linear similarities in the systems, we need to use more deep learning techniques. For example, if we need to consider multi-behaviors of users, as I showed before, different kind of behaviors of click, purchase, view together, and also use different kind of informations, like use the social recommendations, like use some information about social networks, social informations in the recommendation systems. And in those works, this is the basic idea. This is the basic idea about sorry. Yeah, basic idea about why we need to use deep learning in the recommendation systems. I just show some several works of my teams, how we use the design neural networks, deep learning, apply deep learning in the recommendations to solve more complicated, to utilize complicated behavior data. Like actually in this ICD work, and we design a neural multitask recommendations for multi-behavior data. Here the data is we would like to utilize is that we would like to use the interaction data, including the purchase, the final decision. Also, we all need to include in other kind of informations like the add to the cart, or view an item, or other behaviors, or other interactions about the users and items. And the problem here is that if we need to use the information of different kind of behaviors, it's very hard for us to design traditional models like matrix factorizations or other models to consider the signals of different behaviors. But if we use the neural networks, we will do it better. In this work, when we design a system model, like we first design a shared embedding layers to learn the user anti-embeddings by neural networks, and then design a separate interactions of different kind of interactions of different behaviors to predict use behavior. And in the third layer, we call it cascade predictions, predict the use behavior according to those kind of different behaviors. And why deep learning is useful here is that we can more build the multitask training and learning framework to learn the impact or learn the influence of different behaviors. And then we can decide which behavior is more important, or which signal are more important for us to do the recommendations. Yeah, this is the result of our algorithms from the table and the figures. We can find that if we use the neural network deep learning to capture the multi-behavior data of users, we can the recommendation performance will achieve the best over all the performance, and even in different sparsity about the user data, and this kind of algorithm can always have a very good have good algorithm performance. Yeah, I just give a simple examples to show that the deep learning is very useful for including different kind of informations in the recommendation models. Yeah. The second advance in recommendations is the graph neural networks. As you should well know that the graph neural networks is widely used in different areas, and actually in recommendation systems, the graph neural network is also a very important models that we need to consider to design a advanced recommendation systems. As we learned that the first questions we would like to discuss is that why we need to use the graph neural networks in the recommendation systems. As you learned that the basic model for recommendation is collaborative filtering. Yeah. Actually, the graph neural network can help us to build, to capture more important informations about collaborative filtering. The key idea is that the graph can help us to capture high order connectivities about users and items. As shown in an example here is that we have 3 users and 7 items, and the interaction showing in this graph is the edge between user and item. And from this interaction graphs, we can show that the path that reach user 1 from any node with the path length L larger than 1, and then a neutral way to encode the collaborative signal is encoded by the interaction graphs structures. And then we obtain a graph. The graph is including the rows of user and items, and the edge is the interactions, means the user has been interacted with the items before. And from this kind of interactions graphs, we can design.
问到了，你看哪里没关好？
Sorry, yeah, we can design high order connectivities for the user 1, and following the basic idea about the message passing in the graph neural networks, we can capture the high order connectivities for user 1. For example, if we use the one hop information, we can only see that U1 interact with items I1 to I3. And then we can interact with the second hop is that if we the U2 and U3 interact with I1, I3 and I2, then we can find that the other items are relevant to the user 1. And then we can infer that the user 1 may lack item 4 because similar users of U1 and like U2 and U3 also interact with the item 4 with high probability. And the idea here is showing that the high order connectivities can capture by the graph neural networks by the message passing information. Then we can do better collaborative filters. Yeah, they have a lot of works in those 2 years about especially in this years, about how to utilize the graph neural networks in the recommendation systems. And I also would like to show two works of our groups to show that I actually accept the correlation filtering problems. The graph neural network is very useful for us to concede more information in the recommendation systems, as I mentioned before. Yeah, the recently advanced in recommendation system, you need to consider more and more information about users and items, even the relationship about users. Yeah. The first work I would like to show here about the graph neural network used in the recommendation system is the price AY recommendations with graph conventional networks. Yeah, the problem here is that we need to concede the price information in recommendation. That means this is very important, right? When I can infer the price information, have the price information, if I can infer which range of the price you can accept for items, then I can recommend items or product to you more efficiently. Yeah, the most important about the using graph neural network in this kind of design is how to design a graph to combine different kind of information together. Here, we need to concede the price information of our recommendation systems, then accept the traditional user and item loads in the graph. We can concede as the price, then describe the price information into the graph, including the price as a load in the graphs. And then we can design an edge from the item and the price to indicate the information of the price information of an item. And then we can design a unified graph of users, item, price, and category. Yeah, based on this item build graphs, we can use the graph conventional encoder to learning robust representations for different entities. Yeah. This kind of learning algorithms are just can borrow from the latest progress about the graph neural networks. And finally, we have the embedding, learning the embeddings about the user and the items, also the price, and then we can use the embeddings of those three different kind of loads to do the pairwise decode to learn both the global and the local price values about the user. This is just a simple idea about the design, about how to concede the price information in the recommendation system use graph neural networks. And from the result, we can we show here is that our designed solutions relate pop price recommendations can successfully capture users' price values and achieve the best information, best performance compared to the stronger baselines. And can also from this figure we show that this kind of solution can track our cold start problems with help of price values models. That means in the cold start problems, we don't have so many interaction status. We can further use the price information to capture the user preference better. Yeah, this is the first work I would like to introduce. And the second work I would like to introduce is the boundary recommendation with the graph conventional networks. The boundary information is about the boundary recommendation is also a very important problem that we need to recommend a list of items to users together. Then we use the graph to model these recommendation problems. The basic idea is that we need to design new kind of nodes in bundle. The bundle, like in this graph, except the traditional nodes of user and items, we need to design a new kind of node named B in this graph. The B here is the bundle. And then we can design edges in the graph. Like if the item users or items belong to a bundle, then we can add an edge. Then the first step is to construct a heterogeneous graph of user, item, and bundle. And then based on the construct graphs, we can use the graph neural networks to do the item level propagation and the bundle level propagations to learning the representation about users, items, and bundles. And finally, we can design a item level or button level predictions about a user. Then the system can output the bundle information for a user. Yeah, the key idea is that how we can include the bundle information in the graph. And the key design is that we can we can use the graph very intuitively to design the information about bundle in the recommendation systems, and following use the graph neural network to learning the representations and predict the preference of our users. And this shows the performance of the systems. Actually, we can see that the improvement is very high, that mostly greater than 10%, and even achieve 30% in some more than 20% in some cases. And this kind of solutions relate the BGCN achieves the best performance. Yeah, this paper is a CGR short papers, and we received the best short paper mention award in this year's CGR. If you're interested in, you also open the source code for this programs for this work, and you can look for that from the GitHub. Yeah. Another work I want to introduce about the graph conventional network is we also can including different kind of use the graph neural network to conceive multi behaviors of users. Yeah, here the multi behaviors including the different kind of behaviors of click, view, purchase, or some others. And we can use the graph neural network to do the user item propagation to capture different behavior strengths, and use the item to item propagation in the graph neural network to capture different behavior semantics. And the system design is here, and the performance is the best against the state-of-the-art algorithms. Yeah, for this paper, yeah, we also you can look for the paper for the details. Yeah, I have introduced 3 works of how to use the graph neural network in the recommendation systems, and the short summary and takeaway message here is that first we need to design a graph to capture different information in the recommendation systems, and then you use the advanced about the representation learning of graph neural networks to learn high representation embeddings about users and items, and then we can do a high accurate prediction about user preference. For a short summary, for the for the graph neural networks, for the cooperating filtering models, and we can encode high-order connectivities via graph neural networks, and we can enhance the representation of users and items. We can the basic idea is that combine user item bypass graph with other features, like such. In our showcase is we can design nodes about price, bundle, behavior type to learn a few. Yeah, this is the second part of my talk, and the final part is that after we learn about the recent advance in recommendations, I would like to introduce the most important problem of our tutorials is that what's the problem of currently recommendation systems, and why we need to use AutoML for designing better recommendation systems. yeah, for the evaluation of recommendation tasks, and we need to do the product rating predictions, and more important, we with progress of recommendation systems with the industry, we need to use more and more informations. For example, we need to do social recommendations. Yeah, we need to use sequential recommendations, and we also need to do the bundle recommendations. That means the recommendation scenarios becomes more and more complicated, and yeah, and the tasks are getting more diverse in different in those different kind of scenarios. On the other hand, the model we designed for the recommendation is also becomes more and more complicated. For example, in the first generation of recommendation models, the very simple algorithms of simple KNN, we can look at the item similarity and use similarity, use the use level corroborating filtering or item level corroborating filtering. This kind of model is very easy, very simple, and we can design it very well. But currently, if we look at the recommendation system, we use more and more deep learning and graph neural networks, or even including the logic graph in an attention machine design in the recommendations models. Then the message here is that the recommendation models are getting more and more complicated. Combine those 2 points together, the recommendation systems become more and more complicated, and the model are getting more and more complicated. And then the problem for us to design recommendation systems for is that we need to do more and more decisions. The decision including the input features. We need to select important features, and we also need to design different kind of crossing features. And the second step is that we need to design the model architecture of the recommendations. If you use deep learning or graph neural networks, you need to design how many layers of your neural networks and which kind of blocks you design for different factions and to learn a few, yeah. And the third kind of decisions you need to do is the interaction faction design. We have different kind of choice for the interaction faction design. Besides the traditional inner product, we can use like MLP or some other design choice for the interaction, the faction design for user and item. And finally, we have lots of hyperparameter tuning, like embedding size, regularizations, and learning rate in the recommendations programs. Yeah, we have we have so many decisions in those 4 categories that need to design. That need to decide when you design a recommendation models or recommendation systems. Then how we can design such a systems, or how we make such decisions? Actually, first we need to design the system naturally by expect. The expect is the research like us, right? And then we use the experiment or offline data or some online test to evaluate the performance of the system, of the recommendation of the designed recommendation systems. But actually, both of those 2 steps of making decision are suboptimal and inefficiently. The reason is that for the first step, we need to design the model, design naturally by expect. The expect is also intelligence in most of cases, because when I design model by ourselves, we will introduce some noise, like including the unnecessary features. We can miss quantitative integration for the design. For example, maybe we don't know how to design more complicated or lower model architecture. Most important is high labor cost. And the second step of the recommendation system design is to evaluate it by the experiment. This will need large memory and computational cost. Then, moreover, the most important is the low silver bout, that is universal optimal. That means you're in different levels, you may need to design different kind of recommendation system models. And the performance of the different choice on feature or even model or interaction factors or hyperparameters depend on the dataset and task. That means if you have another dataset or another dataset or tasks, you need to design the recommendation system from the scratch. You need to select different models and to select different interaction factors, and the hyperparameter also are different. All those works are needed by human, need to do by us. That means is low efficiently and not so good. And then the problems we can ask here is that how to always make good decisions on different data sets and tasks. Yeah, the solution here is that AutoML. We can, introduced by the Dr. Yao about the basic introduction about the progress about AutoML. We can know that the AutoML can help us to do a lot of things, to help us to do the feature selections, to design the model, and to help us to turn in the hyperparameters. Yeah, I just used the pipeline about the AutoML in the last slide in Dr. Yao's talk, and to illustrate how we can use the AutoML for recommendations. First, from the human aspect, we have massive human effect, and but actually for the if we design automated recommendation systems, it can automatically build recommendation models. And there are 4 pipelines in the automatic recommendation systems. It's from training data, recommendation model design, optimizations, and evaluations. Yeah. For the first phase about feature engineering, or the data selections, the feature engineering is a traditional and task-specific work. The AutoML can help to generate informative and discriminative features. And this is the how to use the training to select the data, or to do the feature engineering. We can use the feature engineering work how to automatically select the features from data. And the second is the model design, or even including the hyperparameter turnings. It requires heavily human and computation cost, and in the recommendation model designs. Actually, yeah, we design different models and evaluate by parameter turnings. It also cause a lot of effect from the recommendation system design. And then if we use the AutoML, it can help us to identify better architecture than handcraft ones. That means the system can help you, if we design a AutoML solutions, the AutoML can select models for us, or even design models for us. Yeah. And the third category about automatically recommendation is the algorithm selections. The more details is the optimization algorithm selections. As well known that optimization algorithm greatly influence model performance. The AutoML can help us to set the right configurations for the optimization algorithms for the recommendation systems. Actually, yeah, this is the basically introductions about why the recommendation system are needed to be automatically, and what's the most important component we can use AutoML to design in the recommendation systems. The basic idea here is that I would like to discuss with you is that in the feature engineering, in the model design, the hypermeter tuning, and finally in the all optimization algorithm selections, we can all those kind of work can are designed in the AutoML areas can borrow to the recommendation system designs. But specifically, for example, give a detailed example is that for the model design for the recommendations, is also not just apply the AutoML method in the recommendations. It doesn't work because for the recommendation models, it has a lot of specific designs. Those kind of specific design you need to consider in your system designs, and then it can be automatically. Actually, in the following of the talk, I will not introduce the details about how we design automatically recommendation systems, but in the following talks of this tutorial, we have some. Actually, we will have two more talks about to show the recent advance in automatically recommendation systems. Yeah. For example, we can use we will introduce we will introduce how we can use the automatic AutoML to do the interaction function design. Yeah, this is the work we published in WWW this year. Yeah, we designed a AutoML method to search the interaction function automatically for cooperative filtering. Yeah, we also introduced the work. We can also use the AutoML to turn in the parameter, as well as the regularization is very important in recommendation systems. And then we design named option. We can learn to regularize recommendation models in our designs. And more importantly, for the feature selections, I mean, some kind of new architecture also designed to select features from the use the AutoML method. Yeah, those kind of details of those work we will introduce in the details by the next tour. But the most information I would like to talk here is that we need AutoML for the recommendation systems because the recommendation scenario become more and more complicated, and we need to consider more and more information in the recommendation systems. So we have a lot of designs, including the feature selections, model design, interaction design, interaction function design, and also finally the optimization algorithms. And we can use the AutoML in this work in those all kind of those phases of the recommendation system model design. Actually, this area is also a very new area that we only have several works in this area, and we have a lot of. Actually, I think we need to do more. Yeah, more problems are still not solved in these areas. And if you're interested, you can, interested in recommendation systems and AutoML, you can look at the different kind of problems, like model, even the model design, even the hyperparameter turnings, or for example, actually what we are doing is that for the embedding size automatically learning in the recommendations is very interesting that if you design a automatically embedding size in the recommendation systems, the performance of this the performance of the recommendation can increase, and the model size can also be decreased. I would like to finally give a short summary about my talks. yeah, I have introduced the advanced techniques used in the recommendation systems, and we can see that advanced techniques are incorporated into recommendation systems such as deep learning graph neural networks and even logic graph. I don't introduce the work about how to incorporate logic graph in the recommendations, but I think we will have a tool later about another talk to introduce how to introduce the logic graph in the recommendation systems. And if we incorporate those different kind of advanced model methods, that we can achieve better performance. And the second point here is that the human craft recommendation system require heavy manual design or computation costs on multiple components, including feature engineering, model architecture design, and algorithm selections. And finally, we come up to the conclusion that the AutoML can help automatically make reasonable decisions on different datasets and different tasks. Yeah, I would like to end my talk here. And in the following talks, we will learn about more details about how to design an automatically recommendation system, including the model design, interaction function search, and also the feature selections. Yeah, actually, if you have some questions, I think we still have several time, like 5 minutes to have some interactions with the listener here.
I have a quick question. So,
okay, please.
Yeah, so great talk. So I'm thinking in terms of like, AutoML can decrease the time to construct the recommendation systems, but I guess how do we still have the problem of evaluating them, right? Like let's say it takes me 100 hours to construct a recommendation system by hand, and then it takes me like 10 hours to do it with the AutoML. But I still have to actually run them and then test them in real time to see like which one's better. So I guess in terms of like evaluating these models is still it seems like an unsolved problem.
Okay, thank you for the questions, and very good questions actually. Basically, the idea here that if we design the recommendation system by human, we need to do a lot of things by ourselves, and it will take like several of months to get advanced models. That means you produce a paper, right? Like just several months, I think, actually. If we design a model, that the most important here is idea is that if we change the data set, if we have new scenarios, we may need to redesign the model again. But if we use AutoML to design the recommendation systems, the model can be actually the time just like several hours or tens of hours can search for a new models. According to our experience, yeah, that means the time cost for the saving how much time we can save is that we use AutoML if we have very just natural computation code resource. We can do that in the time scale of hours or several hours or tens of hours. Yeah, and but okay, yeah, but if we have great computational resource like in Google GPU or some other computation resources, you can accelerate the AutoML method, and then even we can design a recommendation model in several minutes or something like that. But all of them are don't need any kind of human effect, that the system can do it by itself. And then I think the time is one aspect. The another aspect is that it doesn't need our works. We don't need to do it. Yeah, and the system can design the model automatically.
Yeah, I'm just thinking in terms of like the like, for example, let's say you're trying to recommend people to buy an item. So your only feedback is whether your revenue increased.
Mm-hmm.
But so like, if let's say you can build a model quickly, but if that model doesn't increase the revenue versus a human handcrafted model, then
mm-hmm.
it's not really a good model.
Mm-hmm.
So it seems like iterating, constructing models faster is obviously good, but it's only good if you can construct good models faster. But if your feedback signal is like, something like revenue, where you're recommending an item for a user to buy, but it's like your only feedback is if seeing it in a test, right? It's like comparing two recommendation algorithms. You see what I'm saying?
Right. And I get your point. And actually, yeah, you're right that actually you can get some more ideas about how this happens in the automatic recommendation system design. If you will introduce in the next talk, if
Okay.
if I have the details, yeah, you can know it better. Yeah.
Okay, awesome. Thank you.
Okay, thank you. Any more questions? If not, we can turn to actually we need to get some rest or just continue with our talks. Dr. Chen? Yeah. We continue or we get some rest?
I guess maybe we have some rest at the next before
okay.
next one.
Okay, yeah. Cool. Yeah.
Okay. Can you hear me? Yeah. This is today's third talk. I'm Chenggao, PhD candidate from Tsinghua University. It's my great honor to give this talk about recent advances in automated recommendation system. It's a detailed introduction of some papers have been mentioned by Professor Li. And this is the outline. We will present the AutoML-based recommendation system from three aspects. The first one is AutoML for collaborative filtering task, and the second one is AutoML for click-through rate prediction task, and the third one is AutoML for tuning hyperparameters in recommended system. Okay, first one is AutoML for CF. So let's first recap the CF problem. The data input of the fundamental CF problem is a rating matrix with many unknown positions. It's a user item rating matrix. Users can rate items from with different scores. For example, from 1 to 5. The 5 represent the user like item, and the score 1 refers to a dislike. So the task is to estimate the ratings on unknown positions of this user item matrix. And we can use some metrics such as IMC as a measurement on the estimated ratings. Yeah, this is a standard CF problem setting. And the typical CF approach is the low rank models. The partially observed rating matrix O can be well approximated by a low rank matrix X. So we have matrix U for user embedding and matrix V for item embedding. And then we can do the rating prediction by inner product of the user embedding matrix and item embedding matrix. Yeah, so here the interaction function is the inner product. We call it interaction because it matches user with items. So we call it the interaction function. So this is a standard MF model. It's a low rank approach. And recently, there are a lot of researchers propose different and complicated recommendation models. So they use different interaction functions. Here's a table listing some representative interaction functions in different recommendation models. So for the MF model, as I have mentioned at the previous slide, the MF uses inner product as the interaction function to match users and items. And for example, the NCF model, the reference 17, the NCF model uses an interaction function that contains two parts. It contains a multiply. It's a element-wise product between user and items embedding. And another operation is a concatenation that concatenate user embedding and item embedding together. So in NCF, the interaction function contains two parts. So however, there's a question, is there an absolute best interaction functions? The answer is no. The recently published paper found that the models, whether a model is good or not, it depends on the specific task and data sets. So for different tasks, we have different best choice for the interaction function. So that's why we want to use AutoML to help us to design proper interaction function for different tasks. And we propose the SIF approach. And the SIF approach a problem from the perspective of automated machine learning. And considering the design of interaction function, we consider the design of interaction function as a searching problem in AutoML. So we first design a search space. The search space design is inspired by human design interaction functions. And we cut the search space into two blocks, vector level and element wise. The vector level refers to the simple linear algebra operations. Element wise refers to the shared nonlinear transformation. So we can so the human designed interaction functions can correspond to our search space. So it can be considered as a sample or a specific design in our whole designed full space. And sorry. And the search space can be represented with a supernet. So we can see that the element-wise one is implemented by a small multi-layer perception. And the vector-wise one can be seen as a choice on operations. So it's a discrete, we can consider as a discrete operation. And we use S to denote the architecture hyperparameter. It can be considered as a model selection or operation choice. And we use a T to represent the traditional model parameter. For example, in MF, in matrix factorization model, the model parameter refers to the user embedding and item embedding. They are learnable parameters we need to learn and from the training data. So the problem can be here. The problem here can be formulated as a bi-level optimizing task. We have two parts of parameters that requires to optimize. The high level is to optimize S. S is architecture hyperparameters, and the low level is the traditional model parameters T. Here, if we use bi-level programming, it's too expensive. Since here we need a good T. So the good T is defined as the T obtained from the training data. So if we want to obtain a T star, we need to do a full model training. So it's too expensive. So here we use an efficient NAS method. The NAS is shortened of neural architecture search. So we use a model named NASP to approach the two-level optimization problem. So why the NASP is is very suitable for our bi-level optimizing problem. There are two reasons. The first is about the effectiveness. Here we have the discrete architectures for, as I have mentioned before, we need to choose proper interaction function, and the different choices of the interaction function are totally different. So they are discrete choices of architectures. So the NSP is very suitable for this task because it can maintain discrete architectures. And the second one is about efficiency. And another characteristic of an NSP is it can update both S and T in an end-to-end and a stochastic manner. So this algorithm demonstrates the detail of the NSP method. So with NSP to optimize the bi-level optimization problem, we can search a good interaction function and use the search model to and retrain the search model with the training data and obtain the final recommendation performance. So it can be compared with the traditional model because we trained the search model. And first we compared with the method with competitive CF baselines. For example, NCF, and we can also use FM or DeepY to learn from data. So we can find that the SIF is a true best performance. And we can find that the SIF is better than SIF no auto, which do not use validation sets. So here we make a conclusion that the validation sets can help us to search good neural architectures. And we are also concerned about the efficiency. So here we compare the efficiency, the convergence efficiency with other CF approaches. So we can see that the interaction function obtained from SIF can be trained as fast as the state of the art. And there are also another category of baselines. It's about the other AutoML approaches. If we use other AutoML search search algorithms for this task, how about the performance? So here we choose some very competitive baselines from the random search, reinforcement learning-based search, and Bayesian-based search. And we can see that our SF can find better architecture with better recommendation performance, which means the smaller testing IMC compared with other AutoML searching algorithms. We also present the efficiency comparison with other AutoML approaches, and SF is much faster than other AutoML search algorithms. Okay, let's conclude this work. So we design the interaction function automatically, and it can cover both existing human designed interaction functions, and it can also explore some new interaction functions that have never been considered by human experts. And we use one-shot search and update the interaction function and embedding jointly and stochastically. And the results on real-world datasets demonstrate the search model can achieve better performance and compared with the human design models with a slightly higher computation cost. So this work is about how to use AutoML for the traditional and very famous CF task. And another task is click-through rate prediction task. So let's have a quick look at the pipeline of modern recommendation engine. So in today's recommendation system, there are two phases from the all products to a user's recommendation results. The first one is candidate generation, which is also known as the recall phase. Yeah. So the CF model is used here at the first phase, and the data input is the user item interaction data or rating data. You can consider it as as a user item interaction matrix or rating matrix is a matrix data. And then the CF model can learn from such data and infer users' interests. And it can recall hundreds of items from all products. All products maybe million scale. So then we have a second phase. And the second phase is use the click-through rate prediction model, also known as a CTR prediction model. So CTR model is used here, and the data input consists of the rich attributes and the context, such as user profiles, for example, user age or user job, or item attributes such as items price, items brand, items category, or other information. And there are some context information such as timestamp information. So the CTR model can rank the output of the first phase. I mean, the hundreds of items are fed into the ranking model. And the ranking model, the CTR model, ranking CTR model can generate tens of items for final recommendation, because the users in we can only browse tens of items. So this is a standard pipeline for today's recommendation engine. So here we can see that besides the CF model, we have a very important another kind of model, CTR model. So here we focus on how to use AutoML to CTR prediction task. So in click-through rate prediction task, we widely used data is tabular data. For example, here we present a table from the UCI bank data, and we can see that there are some user profiles, for example, user age, user job, and there are some other informations. So they are in tabular form, and we introduce a new term named cross feature. So what is cross feature? For those sparse features in the tabular data, a commonly used manner is to build a cross feature from the raw data. In other words, the cross feature refers to taking cross product of the sparse raw features. So the question is that why we need those cross features? The answer is in two folds. First, it can capture interaction among the category features. For example, job, company, such a second order cross feature. It can be very useful when we want to predict one's income. Yeah, and another reason is that the cross feature indeed achieve great success in real world business. So that's why we need to consider cross feature. And the traditional methods can be divided into two categories: explicit methods and the implicit methods. The implicit methods are more popular and more widely used, such as DeepFM or XDeepFM. These models use deep neural networks to help abstract the cross feature implicitly. For example, feed all the concat all the raw features together and feed them into a multi-layer perception. And then the data-driven training can enforce the MLP to capture such cross features, to find the good cross features. Yeah, so it's implicit because we can control what features to what cross features that can. Yeah, it's an implicit manner. Yeah. So we conclude that there are some weaknesses for these existing methods. So there's no method that can obtain high order feature crossing, high simplicity, and fast inference and interpretability at the same time. So this is our motivation of why we want to propose a auto-cross model that can cover all these strengths. Yeah, it can address weaknesses of existing methods. So the system framework of auto-cross is illustrated as this figure. Here we do not pay attention to the details of the implementations in the real system, such as in last feature, such as the server or any other details about the implementations. We only focus on the core components of the auto-cross algorithm and the flow. The input of our cross framework is the training data and the feature type. And the output is a feature producer that can select the most useful cross features for our CTR prediction task. The core idea of our auto-cross is a two-stage loop. The first stage is a feature set generation, and the second is a feature set evaluation. For the feature set generation, it means generating candidate feature sets with new cross features. Yeah, the feature sets are updated by adding new candidates of cross features. And the second one means evaluating the candidate feature sets. When we generate a feature set, we need to evaluate. So this is the second stage. It's a two-stage loop. And in the second stage, and we need to evaluate them and find the best one to add the new considered cross feature. So it's quite intuitive. And for the first stage, we propose a multi-granularity discretization to build discretized feature of different level. And the beam search is a very important part of our autocross because it can save a lot of time. Here is an example of how we generate a fourth order feature, ABCD. It finds the new candidates in a greedy manner. So when we conduct a beam search, we can for the candidates we conduct a fast evaluation, and we only reserved the feature with the best performance. So it's a greedy search. Another part, as I have mentioned, is a feature set evaluation. So here, to ensure the evaluation is efficient, we use a field-wise logistic regression and to evaluate the candidate's performance. And also, besides to make sure it can handle newly generated cross feature, it works as an online learning manner. So we propose a successive mini-batch gradient descent, which can handle the newly generated feature set candidates. Yeah, so it's a detail of our cross. So here we to evaluate the performance on the benchmark datasets and the real-world business datasets. We can observe that with selecting cross feature by autocross, the LR, logistic regression model, and WND, wide and deep model can be improved significantly because our model plays a role in selecting features. So we can use our AC autocross to L logistic regression or wide and deep model. So when introducing AC, both LR and wide and deep are improved significantly. And we are still concerned about the efficiency. So we present the efficiency of inference. We can find that the autocross computation cost is small. Yes, so for example, by introducing autocross to wide and deep, the inference time is still fun. It's still smaller than XDeepFM. Yeah, that's our first work on the click-through rate prediction. And here comes the third one. How to use AutoML to help tune the hyperparameter in recommendation system. So let's first recap the regularization term in recommendation system. It's a very famous trick or manner to tune our recommendation model. So the core idea is to address the overfitting problem. So here is an example of the famous MF-BPR model. So despite the loss function of the non-reg MF-BPR at the left side, at the right side, we still have an additional part of a regularization loss. It is calculated as the L2 norm of the user embeddings and item embeddings. So the full the whole loss function consists of two parts, non-reg1 and the regularization 1. So there is a common concern of recommended system models. It's about how to tune the regularization term. So we named it as a regularization tuning headache. So for the when we choose different regularization coefficients, for example, from the -9, -12, -6, -3, we can see that the performance is totally different. So for the engineer, Bob, he wants to tune a good recommendation model. Such operations cost him a lot of time to choose a good and proper regularization term for his MF model. So that's our motivation to use AutoML to choose the regularization term automatically. But so why it is hard to tune the regularization term? There are two reasons. First, the traditional methods use the fixed regularization strengths. However, at the beginning of training, when we need a weak regularization to encourage model learning because the data is fresh new to the model. And when we have enough iterations, which means the model have seen the same data for many times, then here comes the problem of overfitting. So at this stage, we need some strong regularization, which means a larger regularization term here to prevent overfitting. So consider this assumption. So the fixed regularization strength is not reasonable. That's another reason. The second one is a compromise of the regularization granularity. Recommendation datasets contains of user item with a diverse set of frequencies, and each latent dimension in our latent model has a different importance. So this means that different regularization strengths might be needed for different parts of the model. For different user, we need a different regularization strengths. For different item, we need different regularization strengths. Besides, for different dimension, for example, if we have a 64 dimension for our embedding space, then we need different strengths for such 64 dimensions. So even though the fine-grained regularization may work better due to the affordable search cost, we resort to over lambda to regularize the whole model because the fine-grained regularization costs too much time. So, for example, the engineers have to choose a lambda to satisfy both users with high frequency and the users with low frequency with the same strength. So it's not reasonable. So we adopt an alternating optimization paradigm to solve the problem, to find a good lambda. So we perform the two steps iteratively. We first fix lambda, optimize theta, and fix the theta and optimize lambda. Here the theta refers to the model parameters of our recommendation model. For example, for MF BPR, the theta refers to the user embedding and item embedding. And the lambda refers to the regularization term. Okay, the first thing we want to is to, so for the first step, it is very similar with the conventional MF BPR. The only difference is that the lambda is fine-grained now. Yeah. So the first thing we want to do is to endow MF BPR with fine-grained regularization, coping with the characteristic of recommendation dataset characteristics. The second step is more complicated. And we use an intuitive manner and we take a greedy perspective, looking for lambda which can minimize the next step validation loss. But how to obtain the theta t+1 without inferencing the normal theta update? Our answer is to simulate the MF update. We first obtain the gradients by combining the non-regularized part and the punishing part. And then we simulate the operation that the MF optimizer will do. So here, the lambda is the only variable here, and the theta is fixed, because here we only consider the update of lambda. So the theta, the model parameter, is fixed here. Yeah, to avoid obscure derivation of the gradients introduced by the MF optimizer and the fine-grained regularization, we rely on the auto differentiation to implement our lambda opt. We first prepare the non-regularized gradients using a simulate forward and backwards on a training data set. Then we use a lambda network. Here we introduce a lambda network. The lambda network's weights is a lambda. So we use a lambda network to do all the mentioned gradient combination and MF optimizer simulation and the computation of a validation loss. So after forward and backward pass of the lambda network, then we can obtain the lambda for next step by the auto differentiation. So the lambda, so when we update the lambda network, we obtain the value of the regularization term of the next step. Yeah, so we can obtain the learned lambda. Yeah, so we follow such steps framework. We can fix lambda, optimize theta, and fix theta, optimize lambda. So we finally can conduct full training with such iteratively bi-level optimization. Here we conduct some experiments on the famous and widely used recommendation results. And we can observe that our lambda opt with fine-grained regularization can achieve better performance. Here the D means the dimension, U means the user, and I means the item. So here DUI means we assign different regularization strengths to different dimensions, to different users, and to different items. So we can see the lambda opt with such a fine-grained regularization term can achieve the best performance compared with some competitive baselines, such as adversary matrix factorization and neural matrix factorization. Of course, our methods can achieve the better performance compared with the MF with the fixed lambda. We can see that the fixed lambda's performance is very poor. Yeah. And we also analyze the lambda trajectory, which means how lambda changes along with our whole training procedure. Yeah, we can have some very interesting and insightful findings. Yeah, first one is the users with a higher frequency are allocated with larger lambda. Of course, and similarly, items with higher frequency are allocated larger lambda. And these two observations are inconsistent with our assumption. Yeah, our assumptions are the more frequent ones can use a larger lambda. And another interesting finding is that as training goes on, as we train the model epoch by epoch, and the lambda gets larger gradually. As I have mentioned before, at the very beginning of our training, we should use small lambdas because the data are fresh new to the model, and our focus is the model training, is to update the model parameter. And after our model have seen the training data for many times, then we should to overcome to address the overfitting problem. So then we need a larger lambda. Yeah, so let's conclude these works. Yeah, AutoML can help us to choose models, choose recommendation models, and it can help to select or generate the data or the feature inputs of our model. Yeah, we have shown the paper that can help to generate the good cross features for our CTR model. Yeah, and the third paper tell us that AutoML can tune happy renders in our recommendation models. Okay, I want to make some discussion. Yeah, AutoML can be used in recommendation for more scenarios. For example, if we have a very complicated scenario, for example, social e-commerce. In social e-commerce websites, users can purchase products via a link shared by a friend. So these scenarios are totally different compared with traditional e-commerce websites. So it's complicated and it's new. So there are diverse recommendation tasks here. For example, we have a traditional task when user wants to buy something. Then we need to design a model that generates the candidates for the user. Yeah, so consider the complicated and new scenario in social e-commerce. We may have some users want to share some products. So here we need a fresh new model that can be suitable for the sharing behavior. Yeah. For example, for another example, some users may want to buy some products together with friends. So it's different again, yeah, because we need to consider the interests of the preference of the user and his friends together at the same time, yeah. So when we have some diverse scenarios with different objectives and metrics, AutoML can serve as powerful tools, and that's our discussion. AutoML can have very high application value because in real world applications, in real world applications, even if we only have one mobile app, there are many recommendation scenarios. AutoML can reduce the human cost and reduce the human efforts in designing proper recommendation models in such diverse scenarios. So these references are the three introduced paper in my talk. Okay, thank you. Any questions? Okay.
Yeah, hi, Chen. Indeed,
Yeah.
I have a question about your talk. Yeah, your talk is very interesting, and your presentation is also very great. I have a question about the utility of the AutoML with the recommendation system, because in practice, the data would always the user's interaction behavior would always will be generated day by day, so which means the property may change over time. So so if we would like to apply AutoML in practice to train a recommendation system, do we need to retrain the AutoML also with the new data coming?
Yeah, I see. A very good question. Yeah. So you mentioned actually you mentioned the weakness of AutoML, but I have a possible solution. Yeah. So in today's recommendation system, one solution to make sure the model can be updated very fast. I mean, for example, hour level, or even minute level updates. Yeah. So they have such a trick. Yeah, they do not update the model, but they update the features. Yeah, so if we find a good model via AutoML via AutoML, we find a good model. So then we can update the input of such a model. Yeah, the feature, for example, feature. And we update the feature in a very instant, in a short time level. For example, we update the features every minute or every day. So it's updated frequently. So the model can reused for example, a week. For 7 days, we use the same model. but for different days, we use different features. So as long as our model are good, we can generate good recommended results with a week level model and day level data feature input. Yeah. My solution is a one possible solution, but I have to admit that your question is it point out weakness of AutoML, and this is also our direction, or the direction of all AutoML researchers. Yeah, the efficiency is always our concern, and we hope that one day the AutoML can update the model in hour level or minute level. Yeah, that's my
yeah, thank you
answer.
Thank you for your answer. Yes, thank you.
Any other question? Okay.
Okay, let's take
let's have a rest.
5 minutes break and come back at 5 minutes later. Okay. Thanks for all. Okay.
Okay, can you hear me?
Yeah, I can hear from you.
Okay, then I can start. Okay, thanks for your interest in this tutorial, and I'm Huan from Paradigm China. And the title of my presentation is Automated Graph Neural Network for Recommendation System. And this is, okay, this is the outline of this presentation. I will briefly introduce some background information about graph neural network, GNN for recommendation, and automated machine learning for GNN. And then recent works on neural architecture search for GNN will be introduced, including 2 types of method, the reinforcement learning method and the differentiable architecture search. And finally, I will discuss some aspects regarding the automated GNN for recommendation. Okay, let's start. As we know, graph neural network has been a very hot topic in recent years, which is powerful for representation learning in graphs. And the key component of GNN is to define the convolutional operation on non-grid data, such as social networks, item graph, etc. And popular applications of GNN includes recommendation and fraud detection, spam detection, and bioinformatics. And in terms of the convolutionary operations, existing GNNs are following a well-known message passing framework, which is that the representation of a node can be learned by iteratively aggregating the embedding of its neighbors. That's what we say about the convolutional operations, i.e. aggregating features from neighbors, and a k-layer GNN access k-hop neighborhoods. Thus, the high-order relation can be exploited. Here, this equation is the key component of GNN. For k-layer GNN, the node embedding the S layer is computed as follows. Note that notice that here, this is the neighborhood include itself. We can see how the neighborhood aggregation works. Actually, for different variants of GNN, we need to design the different aggregation functions like the GCN, normalized sum aggregator, or graph stage, GAT, and GIN, something like this. Okay, and we further give an illustrative example of the computation process. We can see that the k-layer GNN actually are accessing k-hop neighbors, and existing works have demonstrated that the GNN can achieve sold-out performance on graph representation learning tasks like the node classification, link prediction, etc. And speaking of recommendation, we can see that the recommendation problem can be naturally modeled by a graph that can be enhanced by GNN. For example, in the typical collaborative filtering scenarios, as the previous presenter have introduced many of them, we have users, items, and the rating or clicking behaviors. Then a bipartite graph can be designed, and we can then by designing a GNN model, we can learn user and item representations in the user item bipartite graph, where high order relations can further be exploited by stacking multiple GNNs. And further, in modern recommendation scenarios where rich set information exists, such as the category of item or metadata, social network, something like that, and then heterogeneous graph can be used to encode the different type of set information. And likewise, GNN in heterogeneous graph can be designed to learn more accurate user and item representations. In short, the key problem of recommendation is to infer the user and item similarities, which are then used for recommendation. Well, with the help of GNN, user and item representation can be learned accurately. Considering that recommendation systems have been very popular in various applications like the news recommendation, commodity recommendation, business recommendation, and so on, it will be very useful if we can obtain scenario-specific recommendation models, or we can say the data-specific GNN models for recommendation, where the automated machine learning can help. To be specific, the neural architecture search can be exploited to help us to automatically design powerful GNN architectures when processing the graph-based recommendation. And when applying the AutoML to GNN, one important problem needs to be figured out, which is that what can be searched. Let's revisit the message passing framework again. Looking at this unifying framework for GNN models, we can find 4 important parts of a k-layer GNN, including the path of the length, or maybe we can say the number of the hops, the number of layers of GNN, and the aggregation function, which must satisfy the permutation invariant property, and some hyperparameters, and finally the adjacent matrix or the neighborhood. It means we will obtain different GNN models when we define the 4 paths. And in this tutorial, we will focus on method working on searching for different aggregation functions, which is a key component of a GNN model. We will see it later. Now, let me introduce the works on neural architecture search, or NAS, for GNN. Here is the outline of this part. Since we have introduced GNN before, I will give a brief introduction on NAS directly. And the motivation of NAS is to explore the possibility of automatically searching for unexplored architectures beyond human design ones, which have been extensively researched in other areas like computer vision. And by NAS, we can obtain optimal data-specific models in practice. And technically speaking, the NAS approaches follow a trial and error pipeline, which iteratively train and evaluate the candidate architectures from a predefined search space, keeping tracking of the best ones. The figure here is a pipeline of the first reinforcement learning method for convolutional neural network search proposed by Google. To be specific, an ion controller is designed to generate candidate architectures which are trained till convergency, and the validation accuracy is used as a reward to update the parameters of the ion controller in a reinforced manner. The above figure here is the generated layer by layer architecture represented by a sequence, and based on this pipeline, the search architectures can achieve sold-out performance on various computer vision tasks than human design models. And when speaking of the NAS for GNN, in my opinion, it can help alleviate 2 challenges facing existing GNN models. The first one is called the architecture challenge, which is that actually we need data-specific gene architectures in different scenarios. And the second one is the efficiency challenge, which is that the NAS approaches in large graphics tend to be computationally expensive, including the training time and the GPU memory costs. In terms of NAS, it can naturally address the architecture challenge. That is to say, automatically searching for optimal gene architectures when given a specific task. For the second challenge, we design a transfer learning paradigm which searches for optimal architectures in small graphics and then transfer them to large graphics. This is quite efficient in practice, and I will introduce it later. Now, let me introduce existing methods, which are mainly relying on reinforcement learning method. The general pipeline is similar to the one introduced right now, which sampled a child model from a predefined search space and trained from scratch and updated RL controller based on the validation accuracy. There are 3 existing works in the literature, GraphNAS. This is the first framework for architecture search in GNN, and the improved one AutoGNN, a latest KDD publication, Policy GNN, which searches for the number of layers per node in GNN models. Let me introduce them one by one. The first reinforcement learning method for architecture search in GNN is the GraphNAS, whose search space includes the various components of message passing framework, like this kind of sample neighbors, the attention functions, the aggregation function, head number, and hidden dimension set, and nonlinear function, and so on. And in the end, based on the reinforcement learning framework, in the end of the search phase, separate architectures are sampled from the trained ion controller, and then they are trained from scratch. Finally, the best gene architecture is returned as the searched ones. I think this idea is very straightforward and just following the Google's NSNet and the proposed design the RL framework for searching the optimal gene architectures from this kind of search space. And this is the pipeline. Actually, we have an ion controller. We generate the child architectures and train the child models and get the valid accuracy, and then we use it as a reward to update the ion controllers. This is the experimental result of this proposed GraphNAS, and we can, from the net figure, we can see that the RL method can obtain more good models. What is good model? It means the accuracy over 0.81, which is close to the GCN models, and is much more than the naive random search algorithm of the search space during the search epochs. And the red table shows that the performance gain over existing human design GNNs are evident. Okay, this is the first RL work for GNN architecture search. And speaking of another RL work, the AutoGNN, which uses the same search space as GraphNAS, will design a more advanced RL framework for the search process. And next is the attention function, aggregation function, something like that. And to be specific, they split the space into different classes and train an controller for each class. Thus, the update process can be conducted per class or maybe per RN encoder. I think this is the main difference between the AutoGN and the proposed GraphNAS. And for the experimental results, we can see that the performance gain comparing to the GraphNAS is also evident, and this is also the accuracy during the iterations. From my perspective, I think these two works are very close. and maybe they are the first two IL frameworks for GNN architecture search. And here comes maybe the latest work, this year's the KDD publications, the policy GNN, which searched for the number of the layers per node. Notice that in GraphNAS and AutoGNN, the number of layers of GNN is predefined and set to the same for all nodes. And here is the policy GNN, which searched for the number of layers per node in a GNN design. And here is the whole framework of policy GNN, which samples the number of layers per node in the construction of GNN models. And this is the experimental result, and we can see that the performance gain are even significant than previous basenet, including the GraphNAS and AutoGNN. And this is a distribution of the number of GNN layers in the search result. From this figure, we can see that the 2-layer and 3-layer GNN are the most common, which aligns with the fact that existing human design GNN models can obtain satisfying performance in around 3 layers. It is noted that this model can be plugged in different GNN models, while in the paper they use a basic GCN as a backbone in the experiments. It will be more interesting if they can integrate the search of number of layers and other components, like what they did in the GraphNAS and AutoGNN. And of course, in that way, the search space will be too large and the search cost will also be expensive. And now, let's see another type of architecture search method for GNN, which is a differentiable architecture search method. As mentioned before, the RL method, the RL-based NAS approaches are inherently expensive due to its trial and error nature, which means we need to train each sampled architecture till convergence. Thus, this can be quite expensive. And to address the computational cost of RL approaches, the differentiable architecture search approaches have been designed in computer vision tasks. While for the best of our knowledge, this is the first work to explore the differentiable architecture search for GNN. And to be specific, this work has the following contributions, and a novel and effective search space is defined, which are more expressive than those in GraphNAS and AutoGNN. Besides, the efficient differentiable search algorithm is designed, and besides these two contributions, they further design a transfer learning paradigm, which makes the NAS feasible in large graphics. Okay, and speaking of the search space, we focus on the most important part, that is the aggregation function, and design two types of aggregators: the node aggregator, and this is the layer aggregators plus the skip collection. And to be specific, the node aggregators are similar to the ones in GraphNAS, where we add more options like the Gini path, which is a more complex version of GNN models. And moreover, to improve the expressive capability of the backbone representing the search space, we add the layer aggregators, which further makes use of the output of each GNN layers. The design is from the advantage of the residual network in the CNN architecture design. Moreover, in existing work, the JK network, which has demonstrated the superiority of adding this extra layer for GNN architectures. And for each intermediate GNN layer, we further add an option denoted as the skip collection a lot. Thus, we have two more options. The identity means we skip. This is to the final layer for the layer aggregator. And the 0 means we do not skip. And when comparing this search space to existing GNNs, we can see that the search space can cover more existing GNNs than GraphNAS and AutoGNN, like the JK network, the Gini path, and the LGCN, like three types of GNNs. And here we give more details about the node aggregators in different genome variants under the message passing framework. As we have mentioned before, actually the different genome variants is relying on the different node aggregations. After defining the search space, we then represent the search space by a supernet or a directed acyclic graph, a DAG, as shown in the right side figure. Each node represents the hidden embeddings, maybe all the input features, and the edge represents the corresponding OPs operations. From this supernet or DAG, we can see that there are multiple operations between two consecutive layers, which leads to a discrete search problem. We then do some kind of continuous relaxation over the multiple OPs between two layers, for example, like the IJ from layer I to layer J. We define a mixed OP, which is defined as a weighted average of all OPs. This is from the maybe OS, maybe like this kind of ON node aggregator or OS. These three types of OPs. And notice, and here the alpha is learned from data. And for k-layer GNN, after we do this kind of continued relaxation, and the computation process is given here. The first layer is the node aggregator. Maybe here is a 3-layer GNN, and this is a 3-layer. And then this is we need to decide whether we need to skip the output of each layer to the final the extra layer for the layer aggregator. And this is kind of maybe the skip collection of operations. And finally, this is the layer aggregations. And then we can obtain the final representation of each node. And then the problem is transformed to search for optimal alphas, representing the weight of each OPs in a mixed OPs, which leads to a bi-level, this kind of bi-level optimization problem. And I will introduce optimization aggregator. And after we finish this optimization problem, here we introduce how we derive the architectures. We simply choose the OP between each two layers with the largest weight, like this kind of argmax, and then we will keep only one with the largest OP as the search architectures. And this is the algorithm framework. We are using a gradient-based optimization algorithm. Note that we updated the architecture parameters alpha by validation loss, and the model parameters W by the training loss. To save time, we use an approximation step which updates W, and in the inner loop, alpha in one step. In practice, it has been this kind of one-step optimization. It has been reported to work well in the computer vision task, and in our own experiments, we also found it works well for good performance. Here, this is two figures to illustrative example for the searching process. We are updating the alpha, the weight, also the model parameters, and also finally we only kept one OPs between two layers by the argmax. Since it is computational invisible to tune GNN around us in large graphs, we design a transfer learning pipeline which samples a small graph from the original graph to keep the properties as much as possible, and then we run the differential architecture search in small graphics. By transferring the search architecture to large graphs, the performance gain can be guaranteed. Note that here, there is an existing research in KDD 2006 which show that by sampling 50% of the nodes from the original graph, the properties can be kept well. And for the experiments, we have 3 settings. The first 2 is the transactive and inductive, which are the benchmark experiments in existing gene research, and the transfer learning experiment is designed by us, and this is the data set. And for transactive and inductive experiments, we can see that the performance gain compared to the baseline, including extensive genome models, and also this NAS baseline, the performance gain is obvious. And also this demonstrates the effectiveness of the proposed differentiable architecture search. And for the transfer learning task, since only these 2 standard genome models have been reported on this ready data set, which is much bigger than the previous 4 benchmark data set, we compare this as genome baseline, and we can show that the transfer architecture is also better than the graph NAS and also the human design genomes in large graphs. And we further visualize the search architecture on different data sets. We can see that the optimal genomes architecture varies across data set, and not all intermediate layers are needed to be skipped for layer aggregation. Like this kind of, we have no skip collection. Here we have no skip collection. And now we then show the search efficiency comparing to the NAS baseline in 2 aspects. From the bottom table here, we can see that the search cost is reduced in orders, and from the above figure, actually the y-axis is the test accuracy, and the x-axis represents the elapsed time of the search algorithm. And we can see that with time elapsing, the test accuracy of the search architecture is much better than the baseline. These two results show the advantage of the efficiency of the proposed differentiable architecture search. And also, observation studies are further conducted. The first one is we add some random factor to update the weight of OPs during the BP steps in the left figure. The epsilon equals 0 means the proposed differentiable architecture search method, and epsilon equals 1 means the random search with weight sharing. We can see that the effective of the proposed differentiable search algorithm. And the second one is the number of layers. We set k equals 3 in our performance experiments, where explore the influence of different numbers of layers of GNN, and we can see that k equals 3 is enough for obtaining good performance in this benchmark data set. And here is a quick conclusion of this work. We have a novel and effective search space, a differentiable search algorithm, and also a transfer learning pipeline for to run NAS in large graphs. And for future work, maybe the first round we may explore more advanced NAS approaches. They belong to the one-shot NAS approaches, next NSP, ASNG NAS, something like this. And others, we also need to explore the graph-based recommendation beyond the node classification task. And finally, let me briefly discuss the automated gene for recommendation. And besides searching for gene architectures, I think there are 3 important problems unexplored. The first one is how to construct graphs. In practice, we can model the recommendation problem with different type of graph, like the bipartite graph for the user item interactions, and the multi-graph by further incorporating social graphs, and even the heterogeneous graphs by modeling rich set information. Then a direct problem is how to choose this kind of graphs in a real world recommendation scenarios. The second one is how to divide the neighbors beyond searching for aggregation schemas. For example, in heterogeneous graph, we have neighbors in different types, and in a bipartite graph, the neighbors can be in different hops. Then, how to utilize these different neighbors will be a very challenging problem when applying the automated gene for recommendation. The third one is the more severe scalability problem. since in reality nowadays, the binning scale number of nodes of graphs are very common nowadays. Okay, a quick summary. And actually, the Qiang is naturally suitable for recommendation. And AutoML, a NAS, can obtain data-specific Qiang architectures, and automated Qiang can further improve recommendation. As long as we solve the key problem mentioned here. Yeah. This is a reference, and that's all. Thank you. Any question?
Okay. Since the time is limited, so if you have any questions, you can contact with this email for offline discussion. So let's turn to the next speaker.
Okay. Then if you have more questions, you may contact me through this email.
Okay, hi, can you hear me?
Yeah.
Okay. I'm Yong Zhang, a researcher at Four Paradigm. I'm going to introduce our recent progress in automated knowledge graph embedding. The previous talks introduces automated machine learning and AutoML for recommendation system, and also automated graph neural network. Now I will introduce automated knowledge graph embedding. First, I will give an introduction to the background of knowledge graph embedding and its applications in recommendation system. Then I will introduce our two recent works, AutoSF and NRES, that address the important problems in knowledge graph embedding. And finally, I will summarize this talk. The knowledge graph is a special kind of graph that each node is an entity and each edge describes some relation. And the basic units in KG is in the form of triplets. That's head entity and relation and the tail entity, or HRT in short. There can be also many other information like the attributes, types, text information, and ontology or logic rules. Recently, there have been many academic and commercial knowledge graphs like this. Let's see what are important properties in KG. First, knowledge graph is powerful in representing semantic information. We can say that we have semantic
relation, like A is suppose of B, then B is suppose of A, or inverse relations when A is older than B, then B is younger than A. And we can also have asymmetric relations to describe attributes, and also we can have composition patterns. Second, KG may provide various attribute information such as location, time, area, ID. And also as a kind of graph, it can be modeled as a special kind of heterogeneous information network. Then we can mine important properties in KG to benefit our downstream tasks. Nowadays, knowledge graphs have been more and more popular since it has many important applications. It can be applied for question answering, recommendation, medical diagnostic, and anti-fraud. Then let's see how to apply KG for recommendation system. First, we can use KG to describe the user-user interactions by social relationships. For example, if Tom is a friend of Bob, then they may have similar preferences. Then the recommendation system, the recommendation problem of user-item interactions can be encoded by triples with the form user clicks item or user prefers item. For example, besides we have item connections, like we can use attributes and additional information for the KG. For example, if we know the guy prefers the movies directed by Robert, then he may also be prefer the movie for the game. So based on above information, we can see that KG can bring rich semantic and structural information for users and items, and it can explore users' interests more reasonably and offer explanations. Then let's see what is knowledge graph embedding and how to learn from KG. Knowledge graph embedding aims to encode entities and relations in KG into low-dimensional vector spaces. We're also capturing the nodes and edges collection properties. Here is the learning objective. First, we design some model F to measure the probability of triples, and the model have some parameters. Then, with iterative optimization, we improve the performance on a set of positive triples that is in the knowledge graph. We maximize the score, and in the unobserved triples, we minimize the score. So with iterative optimization, we can improve the performance to preserve the important properties in KGs. Then, given a user preferred item, we can use the embeddings and the model F to measure the confidence of this query pair. So based on the background of knowledge graph embedding, and I will now introduce two recent works. First, AutoSF, an automated scoring function searching method. In recent years, there have been large amount of scoring functions designed to measure the probability of triples HRT in KGs. The detailed description are given in a survey of one in 2017. The scoring functions are designed to capture the following important properties in KG. Given a triplet HRT, then the reverse one is TRH. For the symmetric relation R, like the slope is similar to or both. Their scores, the score of HRT and that of the reverse one should be equal. Then for anti-symmetric relation, like larger than hypernym, we require the scores to be negative to each other. We have also different constraints for general symmetric or inverse or composition triples relations. So in general, the scoring functions can have the following types. Translational distance models regard relation as a translation in the vector space from head entity to tail entity. Then it uses the negative distance as a metric to measure probability. Representative works are trans E, trans H, and rotate E, etc. However, these models are proven to be less effective. The neural network models use neural networks like fully connected convolution or recurrent neural networks to model the probability of triplets. But these models are complex and difficult to train. For the bilinear models, they use a bilinear function like this to measure probability of these triplets. Representative works are this most complex analog and relatively simple E. As demonstrated in recent literature, the binary models are state-of-the-art and they are fully expressive. The binary models can be written as a binary function that's H transpose times R times the square matrix R times T. So different binary models have different form of the square matrix R. In order to give a unified representation, we evenly split the embedding into 4 parts, R1 to R4. Then we denote DI as the diagonal matrix of corresponding R. So the scoring function of this mode complex analog and simple E can be represented in the block matrix, graphically represented in the block matrix like these figures. So first, we constrain our limit to the binary model since they are the best among the different types. And then let's see how we can generalize from the given scoring functions, the scoring function in literature, and what are the important properties for binary models. The key problem here is that there is no absolute winner among the binary models since KGs exist with distinct patterns. And then the KGs are sparse and complex, so scoring functions should be well regularized to fit the sparse KG. Third, designing novel and universal scoring functions are gradually becoming harder. So our solution is to adaptively search how to regularize the binary models for different KG tasks with the help of automated machine learning. And in this way, we can design novel and task-aware scoring functions. Based on the recent progress of automated machine learning, we define the AutoSF problem as follows. In each iteration, we pick up a scoring function from a search space script G. Then the embeddings are trained until convergence, and we can get the optimal performance of the scoring function G. Then we measure the validation performance to give the feedback to the structure of optimizer. Then in the next step, we hope the structure optimizer can help us to pick up a better scoring function. Then script G here is the search space. It determines what to be searched. And the structure optimizer is the search algorithm. It determines how to search it efficiently. Then let's see our search space. Based on the 4x4 block forms of the binary models, we can see that they differ in the way of locations from D1 to D4 and also along with their signs. So we define our search space as filling the D1 to D4 blocks and also a 0 block matrix into the 4x4 square matrix and along with their signs. But such a space is very large since there have 16th power of 9 candidates. Then, since it is intractable to search in such a large search space, then let's see how we design our search algorithm to search efficiently. First, we design a greedy search algorithm to progressively evaluate from few blocks to more blocks. Then we have a filter to remove bad and equivalent scoring functions. Bad means that scoring functions have empty or repeated rows or columns. Equivalent means that some of the scoring functions, they have different forms, but they have equal learning ability. Besides, we have a predictor to select the promising scoring functions based on the metric structures like this. The predictor learns a mapping from the structure to performance. The key idea of the filter and the predictor here is to select better scoring functions based on the metric structure rather than train and evaluate the scoring function, because training and evaluate scoring function is expensive here. So you can see that with the help of greedy algorithm and the filter and the predictor, we can dramatically reduce the search space. Then let's see some empirical results. We use 5 benchmark datasets in the knowledge graph area. We use the ranking metric, mean reciprocal rank, and hit at 10 to measure their performance. The larger value, the better performance. As we can see, the binary models are generally better than the other types, but there is no absolute winner among the binary functions. Compared with the human design scoring functions, the scoring functions searched by AutoSF always performs best. Then you can see that the search scoring functions are distinct from each other. This means that they are KG knowledge graph impact dependent, and also they are novel to the literature. As indicated by these tables, they perform differently on different datasets. As for the efficiency, we firstly design a multi-layer perception as a universal approximator to serve as a search space. In such a large space, you can see that performance is really poor. So this demonstrates the reasonability of our 4x4 block matrix, the search space of the 4x4 block matrix. Then we compare AutoSF with the random search and the Bayes search. Obviously, AutoSF outperforms them with the help of domain-specific search algorithms. Then let's summarize AutoSF. Currently, designing new and universal scoring functions are becoming more and more challenging, and different KGs have different properties. We propose AutoSF, the first AutoML work in automated scoring function design. Based on the well-defined search space and search algorithm with domain knowledge, we can efficiently search task-aware scoring functions that perform best perform better than the human-designed scoring functions. AutoSF works on single triples. Then let's see how automated machine learning and or neural architecture search can benefit relational path learning. The relational path learning is an important data structure in knowledge graph. It is formed as a sequence of triples that are successfully connected. In the relational parts, we have semantic information preserved in the triples and have structural information preserved along the path. To avoid abuse of notations, we denote the subject entity as RT instead of H, and the relation as RT and object entity as OT. Then the hidden state is denoted by HT. So based on the relational parts, we define path distiller to recurrently process the embeddings. The input is of the embedding. The input of the path distiller is the embedding of ST and RT, and also HT to propagate the information on steps. Then the output vector VT is used to predict the object entity OT. So in each step, the path distiller focus on one triple ST, RT, and OT. We use ST and RT and the previous information to predict the object entity OT. Then let's see how we design our search space and search algorithm. Here are some examples about how we form the existing models as path distillers. Trans-E here learns on single triples. P-Trans-E learns on learns the composition patterns, but leaves the intermediate entity embedding alone. Qiang and RSN are two recurrent networks that can both process the semantic and the structural information along the path. And we also do a case study to compare the important property in the search space. We designed P1 that process on single triplets, and P2 on two consecutive triplets, and P3 that can learn composition patterns, and P4 that learns fully recurrent, that is a fully recurrent structure. And for the, we use the countries dataset, a synthetic dataset that describes the relations of countries and regions. In task S1, S2, we aim to predict the task neighbors located in, and in task S3, we use neighbors located in and located in to predict located in. So you can see that S1 and S2 predict two hop inference, and S3 is the three hop inference. So S3 is much difficult than S2. As indicated by this table, you can see that P1 and P4, with P1 and P2 perform better in the easy tasks S1 and S2. For the not difficult task S3, P3 and P4 perform better. So different patterns and different models perform differently in different tasks. So here are the main challenges. Since different information perform differently in different tasks, like semantic information is more important in link prediction tasks. For the structural information is more important in entity alignment tasks. But the structural and the semantic information are complex among different KGs. So how to distill the structural information from the relational parts and combine it with semantic information is a challenging problem. Our solution is to design a specific recurrent search space that can cover existing methods, and then we adaptively search the models with the help of neural architecture search for specific tasks. Here is the search space for the path distiller. The input is the embedding of subject entity ST, relation RT, and hidden state HT-1. Then we output the VT to predict the object entity and propagate the hidden state. So we use operator 1 to process the entity embedding S1, operator 2 to process the relation embedding RT, and operation 3 to get the output embedding of VT. Then we use 4 chosen 1 selections to control the connections among different operators. The left part focus more on the structural information by selecting collections. The right part focus more on semantic information by searching combinators and the activation functions for each operator. So our search space is formed in the by the connections, activation functions, and the combinators in this figure. So before presenting our search algorithm, let me first introduce the neural problems in neural architecture search. As a neural architecture search problem, we have two main considerations. First is the evaluation problem. Since the evaluation gives feedback signal for each architecture, so this is important. In a standalone approach, we separately train and evaluate each model. This approach is reliable. This approach can give reliable feedback for the architecture, but this is very slow since each model needs to train into convergence and they are separately trained. In the one-shot approach, we firstly build a supernet like this, and the supernet covers the architectures in a search space, and different network architectures are evaluated inside the supernet. So different architectures share the parameters in the supernet. The one-shot approach is efficient but not reliable, since when sharing parameters, the architectures may perform differently than their own learning ability. So the second one is the gradient problem, which offers optimization direction for the architecture. Generally, the gradient information should be obtained from validation environments. However, the ranking-based validation metrics used in knowledge graph is generally not differentiable. So we cannot give direct gradients to learning architectures from the ranking-based metric. Let's say our solutions. For the evaluation problem, we observe that the feedback signal from the one-shot search do not necessarily correlate. The correlation between one-shot search and the standalone search is weak. Like in these figures, you can see that the models that perform better in one-shot approach does not necessarily perform the best in the standalone approach. So this means that training and evaluation architectures in the supernet with parameter sharing is not reliable. So instead, we use the one-shot approach. We use the standalone approach. Then, for the gradient problems, since the evaluation metric in knowledge graph is not differentiable, so we refer to derivative-free methods, such as reinforcement learning and the reinforced gradients and the natural gradient descent. So in this paper, we use natural gradient descent, a second-order method that is stable and also has convergence guarantee. So empirically, in the entity alignment task, we compare NRAs with different models on the 4 benchmark data sets. You can see that the models focus more on the structural information performs better than the models focus more on the semantic information. This means that structural information is more important in this task. And NRAs is able to search models, search the architecture, perform best in the 4 different benchmarks. And the search models have different forms. In the link predicting task, we have the similar observations. One interesting observation is that you can see that the WordNet 18 dataset has more one-hop query triples in the validation testing data. And for the free-base 15,000 data sets, they have more two-hop triples. So the search models in WordNet 18 process the single triples, and the free-base 15,000 process two consecutive triples. So this means that the search architectures adapt well to the given data set. Finally, the efficiency of NRS is guaranteed by the natural gradient-based algorithm. It is better than the first-order method reinforcement learning, and better than the Bayes optimization. Next is summary. When learning relational parts, when and how to leverage structured information is task and data dependent. We firstly explore the difficulty and the importance of such a problem-dependent problem. And then, based on the neural architecture search, we propose a domain-specific search space for recurrent neural network and use natural gradient-based search algorithms to search efficiently in this search space. In conclusion, knowledge graph embedding is the hot topic recently. We take one step further to consider automated knowledge graph embedding. We have AutoSF to design task-aware scoring functions by greedy search plus domain properties. We also have NRS that works on relational parts, so natural gradient plus domain properties. As for future application recommendations, we can use AutoSF to search scoring functions that directly work on the triples user preferred item to give direct prediction, or we can use NRS to give explainable inference through relational parts. Thank you all. Any questions?
Okay. Okay, thanks everyone. And this is the end of today's tutorial. And if you have further questions, please visit the following GitHub page. And you can also send questions to the following emails. Thanks everyone.
Thank you. Bye-bye.
Thank you. Thank you. Bye.
Thank you.